Okay, continuing on today with our playlist on the principles of the definite integral. We have here the integral from 0 to 2a of f of x dx. This can be broken up as two integrals, the integral from 0 to a of f of x dx plus the integral from 0 to a of f of 2a minus x dx. But now the interesting thing about it is, this second integral, you just notice this is a lot like King's principle. If we started with this and we add the bounds together, we get 2a minus x. That's our substitution for King's principle, but notice the bounds change. We just have a for this upper bound here. This principle actually works well with the first two videos I did in this playlist because it kind of leads, if you use this, it leads to those other two videos. In order to show this, what I want to do to get started is first I'm going to just break this up. We see we kind of want it broken up, so let's take this first part on the left, and we can of course break this from 0 to a f of x dx, and then we already have our first piece just by doing that. But now for our second integral, we need to break this all the way to 2a, so this is going from a to 2a f of x dx. But now we already have the first part, but this part here looks a lot different than this. We kind of need to get this one into this form. What I want to do for this is a u substitution. We'll do u equal to 2a minus x, and I also can solve for x, so if we do that just rearranging, we have x equal to 2a minus u. I'll take a derivative, we end up with dx equal to minus du, and then we'll just go ahead, just working on this piece here, and let's try to simplify this over here. So let's make the substitution, plugging 2a in here, 2a minus 2a, so our upper bound is going to become 0, plugging a in here, the lower bound becomes a. Then for our f of x, plugging in this value we're going to have, this is going to become f of 2a minus u, and dx is going to just be minus du. But then I can take this minus sign and bring it out front of the integral, so let's use that. But what that allows us to do is just flip the bounds. So when I do that, now we're going from 0 to a, and that's good because that's kind of a piece we wanted right here, right? We want this to go from 0 to a. But then from here, all I need to do is a variable change on this. It's a definite integral, so I can change this back. I'm going to change it back to x because in our final result, everything's in x. So let's just rewrite this all in x. We're going f of 2a minus x dx, but that's exactly this part here. So let's just take that and put it back in the integral just to show it. And so like I said before, this is actually the exact same as this. So now we've shown that our integral can be broken up like this, but then what is the value of this? When do we use this? Well, honestly, I don't really know all the scenarios, but I can relate it back to a couple of the earlier videos. So kind of just focusing on this second piece. One case is if we have f of 2a minus x, if this is equal to f of x, well, if that's true and we plugged f of x back in here, then this integral is the same as this integral, and we end up with 2. We can bring 2 out front, so we got 2 copies. The integral from 0 to a, just f of x dx. And we showed this principle in an earlier video, which is kind of nice because all it does is it kind of takes the bound from 2a and it kind of splits it in half and brings a 2 out front. So this can be pretty useful. But the other scenario we have with this second part is what if f of 2a minus x, what if this is minus f of x? Well, that's pretty nice too, because if you take minus f of x, you plug it back in here, we have this integral minus itself, and then the whole thing becomes 0. So this here was another principle we found and a quick way to find that a whole integral is just 0. Okay, there you have it, another interesting principle of the definite integral. Thanks everyone for watching. Have a good day.